Hi folks, here's a quick video about biodiversity and a way you can quantify it. So we're going to be learning about this equation here, which is called Simpson's Index of Diversity. So you should by now be familiar with the concept of what biodiversity is and how it could potentially be measured, how you might be able to compare it. So biodiversity can be considered at three levels. You've got obviously genetic diversity, which refers to the number of different alleles within a population. If everyone is a clone, then you don't have a lot of genetic diversity, but if there's a lot of variety out there, then there's more diversity. Species diversity obviously refers to the number of species in a given location. The more species there are, the more diverse it is. And then at a sort of higher level on top of that, the more species there are, the more likely you are to have different habitats in a given region. So, for example, the Amazon rainforest is a particular habitat, it's a very diverse habitat. But in South America, you have lots of other particular habitats, grasslands, mountainous terrain, semi-desert areas as well. Okay, so habitats are diverse as well. So this is summarised here, what those three terms mean. But what we're interested in is being able to go into a given region, compare the two, and actually come up with an idea of which one is more diverse. So if I pop these photos up here, get you to think about which of those is the more diverse. Well, you might struggle to do that. I've done this with my classes and they all settled for this one here. This is a kelp forest in the Pacific Northwest of the USA. And although it looks really exciting because you've got lots of really busy plants growing up there, actually it's not very diverse. Here you have kelp, maybe a couple of sea urchins and an otter. Whereas here, this is particular bushland in South Africa that's considered really, really diverse. There are thousands of different species out there. So it can be difficult to do it just by looking at a habitat. So we need to come up with a measure for how diverse a region is. And to be called biodiverse, you need these things, lots of different species and kind of large and similar numbers of each species. If you have a habitat that's completely dominated by one type of plant, and although there are others in there, they're only ever found in ones and twos, you can't really call that diverse. So we're looking at evenness as well as richness. Okay, so species richness is obviously just the number of species in a habitat. Evenness is the number of individuals, so that you can't have one species with thousands of individuals dominating and the others just sneaking in around the edges. That wouldn't be truly diverse. Okay, so in order to get biodiversity, we need a balance of those kinds of things. And we're going to go through a worked example for how you might be able to calculate this. If you collect some numbers, go into a habitat and actually count up the number of individuals of different species, we need to be able to compare the sort of biodiversity of those two habitats. So here are some made up numbers. We're looking at a habitat that's got 3 flowers in it, daisies, dandelions, buttercups. Just by chance we happen to have 1,000 in both habitats, but you can see habitat 1 and habitat 2 are very different. Here they're quite evenly spread. There the buttercups appear to be dominating and these guys are just sneaking in around the edges. So we'll have a look at whether or not there is a difference in biodiversity. They both have the same species richness, they don't both have the same species evenness. So what we need is a mathematical way of kind of quantifying this, turning this into a number so that we can actually compare the biodiversity. And this is where Simpson's diversity index comes in. It's a calculation and it takes into account both species richness and evenness, but just be warned, if you go out there and start Googling Simpson's diversity index or pick a textbook at random and look it up, you are going to find different calculations because Simpson's diversity index isn't actually one index, it's about 3. And they all do the same thing, but they do it in slightly different ways. And you've got to be really careful that you only use the version that your exam board AQA specify. And it's the one they actually list in the spec. So this one here and this one here, ignore those ones. They're the same kind of calculation, but you need to steer clear of these. So if you see an equation that looks like this, don't use it in a textbook or online. And this one here looks very similar to the one we're going to use, but it's actually upside down. Now the reason we're avoiding these two is that these are going to give you values between 0 and 1, with 0 representing infinite diversity and 1 representing no diversity, and that's nonsense, isn't it? That's bonkers, because surely the higher the number, the more diverse it should be. So these two give you a measure that isn't very, very useful at all. So I'm skipping over those, and I'm going to point out that we're going to use something called Simpson's Reciprocal Index. You don't actually need to know it as that. We're just going to call it Simpson's Diversity Index, and it looks like this. Okay, this is the version we're going to use. Just notice the difference with that one there. It's the same thing, but upside down. So you need your sigma n-1 on the bottom here. Okay, so let's have a little look at what we've got in this equation. It looks scary at first sight, but it actually isn't. So on top, you've got big N times by n-1. This is the total of organisms of all species. So if we were to go to our daisy example, there we go. If I was looking at habitat 1, well, we've got 1,000 individual organisms of all species. So my big N in that example is going to be 1,000, and n-1 is going to be 999. This little n here is the number of organisms of a single species. So let's go back to those numbers. Okay, let's take daisies. I've got 300 daisies, so my little n for daisies would be 300, and my little n-1 for daisies would be 299. But as you can see, I've got 3 species, so that's why we've got this sigma sign here, because what you're going to do is you're going to work out little n times little n-1 for all the species, and you're going to add them together. So far, I've talked about a lot. What does that actually mean in terms of the numbers? So we're going to do a calculation, a worked example. But what you've got to remember, when you get your results, a low value of diversity of this index would suggest that the habitat was dominated by a few species. That means it's not going to be resilient to change. If it's just grass, any change in conditions that means grass can't survive there is going to kill everything in that environment. Generally speaking, more diverse habitats are more resistant to change. Okay, so back to the worked example. You've got to do them one habitat at a time. So we're going to take habitat 1, calculate our Simpson's diversity index for that. Then we're going to do habitat 2. So here we go. Got the equation over there. Just have a look at how I'm going to work it out. First thing I'm going to do is I'm going to work out little n times by little n-1 for each of the 3 species. So here we go. That's 300 times 299. 335 times 334 and 365 times 364, and those are the answers there. You can check my working on your calculators if you like. We've got to add them all up. That's our sigma bit. So now what I've got is sigma little n times by n-1. I've calculated that over there. We've now got to do big N times by n-1, which is going to be looking at our 1,000. So we're going to do 1,000 times by 999, which gives us this down here, 999,000. Okay, so that is effectively the number that's going to go on the top of our fraction. So when you plug those numbers into the calculator, you will get a value of D, which is 2.99. All right, let's do the same with habitat 2. This should say 2 over here. I didn't correct that when I put it in, but just remember that's a 2. What we've got here, again, we're going to do n-1, so 20 times 19, 49 times 48, 931 times 930, those are the numbers. Add them all up, we've got 867092, that's the bottom of our fraction. We've got big N minus 1, so that's again 1,000 times 999, that's the top, so we're going to do 999000 times by 867092, not times by, divided by 867092, whoops, and you're going to get this number here, 1.15. So if we were to compare those two numbers, this one obviously is smaller than when we did habitat 1. So it's pretty clear that this one is not as diverse. And actually, all this is doing is telling us something that was immediately obvious. This habitat is dominated by buttercups. It's not as diverse. All we've done is put a number on it to prove that. Okay. So that's how you calculate Simpson's diversity index. Be careful to use the right version of the equation. Be methodical. You've got an example you can do in your booklets.